is a series of valuable knowledge and use cases that we are able to succeed and accomplish into this project. First of all, it's a privilege and honor to welcome you to today's event. My name is Bogdan Stroie. I am a project manager for EUROCC Romania. EUROCC is the project behind all of this. It is funded by the European High Performance Computing Joint Undertaking. And our mission was to build a network of 34 HPC, high performance computing competence centers across Europe with the project which is called EUROCC. CC comes from the competence center. So we are a network of 34 competence centers across Europe. And our mission is to address the gaps of skills and competences and expertise across the countries. We are here to help users with education, with trainings, with new skills, and with access to resources which are provided within this network. So our mission here is to help you, to assist you, and to support you in promoting this implementation of best practices in high-performance computing. So that is why we are here. We are collaborating each other very tightly. And today, together with NCC France, NCC Spain, NCC Austria, and NCC Netherlands, we are co-hosting this event. Our let's say purpose for today is to bring it in the front of the lights some real-world applications that we managed to accomplish during our cooperation in the last year. So it is a pleasure to be here today and talk about something, bless you, something that is rapidly transforming the industries across the globe. A little bit about the context. This high-performance computing, which works very well hand-in-hand with artificial intelligence, not only, it doesn't matter in what industry you are, in healthcare, in finance, in engineering, in any other sector. HPC, it's a sorry. Please, can you mute yourself? Okay, thank you. It doesn't matter in which industry you are, healthcare, finance, engineering, HPC brings you the ability to access a powerful computational resources, which is no longer a luxury. It is actually a necessity, I would call it. So let's explore today some examples, some ways of how HPC technologies can lead to new opportunities, have accelerated innovations, and maybe they transform business and why not research organizations to a more and more mission and successful mission accomplishment. So HPC is about using supercomputing and advanced computational techniques to solve complex problems that otherwise would be impossible or would take a lot of time using traditional computing methods. And today we have a couple of showcases that actually benefited from using this kind of resources, scaling the operations, improving the accuracy of algorithm and models, enhancing the product development, and why not keeping the business competitive on a fast developing markets. We are working together into this field. We are bringing together experts in the field of HPC that make everything possible for the users in different countries to gain access not only to the infrastructure, but also to the expertise, to the professionals who can guide you in the best usage of these technologies. Yes, because you cannot simply use this kind of resources if you don't receive consulting, education, and access to training opportunities. So for that, please stay connected into our community to find out more about all of our initiatives, because the project will go on. It's not the end of the project. We will still be here to continue this mission. So having said something about the context, we invite you today to take full advantage of the resources and the knowledge that we are going to provide today. It is either they will inspire you to encourage you to adopt HPC in your business and in your projects, or who knows, to find out more opportunities about potential partnerships, new collaborations, and new insights. So first of all, I would like to again to thank the contributions of competence centers in France, Netherlands, Spain, and Austria, together with us from Romania, in this beautiful project. We are closing one successful year. This kind of competence centers are actually the engine and the core behind the empowering these industries, the research, and also the public administrations with access to HPC and artificial intelligence solutions. And our agenda for today will begin with an exploration of the machine learning open source ecosystems. And after all, we are going to showcase some of the successful stories which were developed in the past times, especially this year. I would like to introduce our first speaker for today. It's PhD Laure Bourgeois, Miss Laure Bourgeois from France, from NCC France. She is an expert in AI and digital simulations. She has more than 22 years of experience in R&D and is also commissioned by the training organizations and universities on deep tech subjects. She joined INRIA as part of the NCC France as an engineer and also a trainer in this project. And she is also teaching in the University of Versailles as a master's degree program on AI. So welcome, Laure. Thank you very much for being here and starting this series of presentations and speeches of inspiration and collaboration into our event. And from now on, you have the word. The floor is yours. Thank you again for being here, and I'm fully convinced that it will bring a lot of value and a new insight in the forefront of our participants today. Thank you, and you have the lead.
Thank you, Bogdan. Can you hear me, everybody?
Yep, we do.
Yes.
Loud and clear.
It's yes. The sound is nice. Okay. And firstly, I'd like to thank you, Bogdan, and I'd like to thank the TerraTech Association and the NCC Romania, especially Andrea Dinu for the organization, and Karim Azoun from TerraTech, also Carmen Elena Sirnou, well, and Bogdan today. So today we are going to address the following topic: machine learning open source ecosystem, and we are going to make a focus on Scikit-learn and HPC. First of all, I'd like to know if anyone has knowledge about AI and in particular Scikit-learn, because for me it's important for my talk. So can you put it in the chat if you have some knowledge in the Scikit-learn ecosystem, or
I think putting in the chat or reacting somehow with the
or reacting. Alors attends. Alors yes, some okay. React. Yes. Okay. So some of okay, so some of you have knowledge about Scikit-learn. So I will. It's a disclaimer. I will because I see that some of you didn't respond, and some of you don't have any knowledge about Scikit-learn. So I will explain what is Scikit-learn. Well, my time of presentation is 1 hour and a half, Bogdan, with the question.
Yeah, according with the agenda, yes. If you think it is too much, we can adjust. We also started a little bit later. Okay. It's up to you. If you need 1 hour and a half, it's fine.
I think it will be less.
That's perfect then.
A little less. Okay.
Feel free.
And we can make a discussion. So okay. So I'm going alors, my slide. Alors, écran partagé. Tac, tac. Do you see my screen?
Yes.
Okay. Okay, so let's go. So what we are going to see today is a mutual issue between AI and HPC, AI in general, benefits of using AI, especially machine learning through some use case in the perspective of HPC, some principle and basic notion of machine learning. It's why I ask if a participant knows Scikit-learn. And after, I will give you a global vision or several global vision of open source machine learning ecosystem in HPC context. After, we will make a focus on Scikit-learn, the INRIA, French National Institute of Numerical Technology. So INRIA, Scikit-learn is the INRIA Big Tech. It was initiated by INRIA in 2007. And then if we have the time or if you want some practical example. So, and conclusion about issues. So, as you all know, you have mutual interest of AI and HPC because HPC provide new opportunities to push the boundary of AI, and AI may give new opportunities to push the boundary of HPC, what supercomputers can accomplish. So what AI can bring to HPC? First, it can accelerate, understand and optimize, drive and monitor. It can be used for safety and sustainability. And the idea is the combination of AI and HPC make it possible to improve the capabilities of the computer system in terms of calculation speed. And AI can also be used to understand HPC computing application and system. And for sustainability, the aim is also to decrease food carbon print and energy and impact. You can, if you want to make it more interactive, I think it's maybe a good idea to make interruption if you want it. I don't know for you, Bogdan.
Well, I think it's okay to proceed like that. I would not change the, yeah, please go ahead. I think it's okay. It's fine.
Okay. Okay, so it's fine. So AI can reduce HPC energy consumption by activating different levels. So resource allocation, because resource allocation problem is one of problem of AI. AI, I will make is a non-contractual definition of AI from my point of view of AI. So from my point of view of AI, resource allocation, it's a problem of AI. And AI can reduce HPC energy consumption in order to predict computing demand, monitor component temperature in real time, and prevent and avoid breakdown. So detect the first warning sign of a failure by detecting a component before its breakdown. Sorry, I have a echo. Willie?
Yeah, please, everybody who is not a speaker should turn off the microphones because we have some additional effects. Thank you.
Okay, thank you. So let's take an example. As you can see, if you want to optimize the overall performance, you have to optimize scalability, calculation, performance, and parallelization. On the other hand, parallelization. No, I'm sorry. Sorry for my English. Parallelization performance. And knowing that parallelization is a resource allocation problem, and as I said before, it is a part of AI problem that AI can address. On the other hand, what can HPC can bring to AI? So it can speed up processing by performing distributed computing, and speed complex calculation with large amount of data, especially in computer simulation modes. So because as data set grows in complexities, so do the same the computer demands of classification techniques, and so we have to enhance machine learning efficiency without compromising accuracy. We will go more into details later, and we can take some techniques as parallel processing, distributed computing, and cloud computing. For instance, parallel implementation of matrix operation, gradient calculation, and optimization algorithms have been developed to exploit multi-core architecture. And you have difference between parallel and distributed algorithm methods. And but I will not go into details here. And but you have to caution with the parallelization with distribution, as you know, because when you transfer data, if there is a breakdown, you could have a problem when you are going to recover from machine failures. So how to parallelize machine learning algorithm? And let's go to a use case. So not all machine learning algorithm can maybe parallelized or distributed. Only stateless feature extraction, cross-validations model. It's why I ask you, but I will go more into details later if you want it. Selection model with grid search, and a meta algorithm as a bagging model. One of these meta algorithms is a random forest, and this random forest is an easy model to parallelize. But what you must to watch out, because you can't parallelize iterative model like boosting models. And you have to watch out if the computation you disrupt is too small. And I will put ecosystem with related to this methodology. So let's go. As you said, you have different use case in AI. So I will just go for people that don't know a lot of AI. One of the application of AI. So if you want to segmentate some use case, for instance, marketing, you have KPI, recency, how recently a customer has made a purchase, frequency, how often a customer make a purchase, monetary, how much money a customer spends on a purchase. And so you have some data, I mean the sell histories. So you are going to make some treatments, machine learning, supervised or non-supervised machine learning. And it could be also deep learning, but we are not going into details into deep learning today. We only focus on machine learning, not deep learning. And the output is computer group identification. Sorry. Sentiment analysis, it's also possible, and a natural language process it can be distributed on supercalculators. And yes, here you have French comments. French comments I have on the social networks. And here the use case is a French store. And well, the comments in any case in France are often contradictory. And the problem is to understand if what you are going to choose between negative feeling in red and positive feeling in green. You can also use machine learning to detect anomalies, and we want to extract aberrant data which deviate from a normal law. For example, a cat-meter woman is an aberrant value in a demographic data. And in this case, the isolation forest algorithm make it possible to detect aberrant values. And we want to detect what is the threshold, fixed or adaptive. So it can be applied to fraud detection. So you have also KPI. We start with the same methodology. You have KPI and data and processing, supervised or not, and the output. The use case is different than marketing, but the structure and the approach is identical. So now to converge HPC of an AI, I remark that the 3 V of big data, volume, variety, velocity, and value. I didn't put value and I didn't put veracity, but these 3 V are the 4 key driver of the big data revolution. And a way to treat them is for the volume to make some batch processing, for variety to use NoSQL database, and for velocity to use real-time processing. So for all of this, you can use HPC and AI. For the veracity, it's rather a consequence of the data collection, but as you know, it could be a consequence of architecture of the cluster, if it's asynchronous or not. So in AI, you have 5 modes of analytics. You may want to describe your data. You may want to analyze in real time, gives insight into the minutes of analysis, and you may want to make a diagnostic, or you may want to predict some data, or to make some prescriptions. The problem of making prescription is a very difficult problem in AI. So here we will just go into the problem of doing prediction and not a prescription. So what is the case if you need for machine learning? If you need for machine learning, you are in the case that data is cheap and abundant. Knowledge of human is expensive and scarce, and human expertise does not exist, or they are unable to explain their expertise, or existing solutions are expensive. So in this case, you can use machine learning algorithm. Why I say that? Because it's not always the case that you need machine learning. and there is no need for machine learning. Your process is very simple. No data, or data is too difficult to acquire, and you have high stakes decision in criticality context or business intelligence is suitable. So I'm going to go into a principle and basic notion of machine learning, but I would like to first ask is people know machine learning concepts, because if everybody knows, I will pass this part. So do you have a notion of machine learning, everybody? If there is someone that don't have a bit, yes, okay.
Maybe you can make a short
okay.
Yeah,
okay.
familiarization with the
Yes.
concept. I'm not expecting everyone to have a deep understanding of machine learning concept, but just a little bit of, yeah, thank you.
Okay, so this slide, what is AI? It's non-constructor slide. On the one hand, you have symbolic AI with automated language processing, but with a symbolic approach. You have also multi-agent system or expert system and planning, automated theorem proving, and automatic diagnostic. So to simplify, you have this is one part of the AI, as we call them the symbolic, and the other approach is to make an approach with a statistic and data based on data science. And you have machine learning, and inside you have supervised and non-supervised, reinforcement learning, and inside you have deep learning and neural network. What I want to point out here that this slide is not contractual first, but each brick can be used with other bricks. So there is no antinomy, from my point of view, between multi-agent system and machine learning, because some machine learning algorithm could be inside a multi-agent system and so on. So if you know, I will just go to, so you have artificial intelligence, machine learning, supervised learning is to make some cluster, and to make some classification and regression, and unsupervised learning is to make some clustering. So I will not go into details. So now I will go in the core of my talk. And the idea is to give a global vision of open source ecosystem to be operational. Okay. So if you take, for instance, an architecture example, you have, if you want to make an application in general, you need some distributed event log and queues. And you need to put in stream processing, and you need distributed storage, and you need distributed batch processing. And after, you need online transaction processing, and then predictive model and an analytical database. Well, this is a global architecture. Could you share application? Okay, yes. So this is one example, and so I take the same architecture, and I put some technologies behind. I full the architecture with some technology. So as you know, I think you know Spark. You can use Adobe, Spark, Flink, and to interact to make distributed events, distributed storage, and distributed batch. And for online transaction, you could use Cassandra, and Scikit-learn is just a brick inside. Now Spark has a brick of machine learning also, but you can isolate machine learning algorithm for more transparency. And there is another architecture example of when you use Storm for distributed event stream processing, and HBase for online translation, and Redshift for analytical database. So since I say that, I will go more into detail into the Scikit-learn ecosystem. First, I make a focus on Scikit-learn ecosystem, and after I will make a different focus on all these technologies. So do you know all this? So you have Scikit-learn, but do you know all this name? Cores, Crub, Joblib, Fairlearn, Embellished, Learn, Zardus, and persisting. And what is the name of this? And Joblib. Do you know all this library? Okay. No, okay. So, well, not at all. Okay. So mostly, Herrera, you know. Herrera, no. Okay. Scikit-learn only. Okay. Well, so it's why it's interesting to make a focus on the ecosystem. So I will make a focus on the Cores ecosystem. Cores is to connect categories emerged by Scikit-learn. So I will make a focus on Cores. But here this is a Scrub is for prepping data. It's compatible with pandas and polar data frame, and it can work on heterogeneous type, numeric, categorical, DATs, text, and missing values. So prepping, so Scrub for prepping data. Joblib, I think you know, it's a set of tools to provide lightweight pipeline in Python. And it is optimized to be fast and robust on large data. So it's to parallelize in with several core. And Fairlearn, imbalanced LAN offer a number of techniques commonly used in dataset, showing if it is the case that data are imbalanced. So you have to take in account that. So with this library, you can deal with imbalanced data. For instance, there is in France, there is only 20% of women in computer science. So you have to deal with that if you want to make some statistics. And Fairlearn is to monitor and mitigate the responsible risk about Scikit-learn algorithm. You have also Hazardous, the aim is for analyzing risk. And you have Scope, sorry, I missed a P. Scope is to persist models. So you train models, and after you extract this model, and you compress with this model with this library. And well, maybe you know this ecosystem. Who knows this? Red, Dask, Joblib. Okay. One API I have used slightly. Okay. So one API is an open standard by Intel. It's an API intended to be used across different computing accelerators, architecture, including GPUs, AI accelerators and field programmer gate array. You have Rapids that provide unmatched speed with familiar API. And so Rapid is built on the state-of-the-art foundation like NVIDIA CUDA and Apache Arrow. You have also Ray and Dask. Ray and Dask is to distribute treatments in a cluster. So they are doing the same job, but Ray is more performance because there was some benchmark with, for instance, ADA Boost. We did some benchmark. But Ray is less performant, but no, sorry, Dask is more user-friendly, but Ray is more performant. So, and in fact, you can use Dask on Ray. So you can put Dask in Ray. So this is another brick. And back to machine learning. So an overall global interactive process. CORES is for iterability. And so CORES stands for Conceptual Research Search Engine. It is a RDF, Resource Description Framework, based on a conceptual graph. Does anybody know the conceptual graph here, or knowledge graph? Yes. Okay, a little bit familiar. Okay, graph neural network. Okay, so what is interesting is once you have make your cluster with machine learning, with Scikit-learn, you can connect them with CORES. So you can first make clustering, and then CORES will give you a knowledge graph on the top of the brick of Scikit-learn. And data cleaning, because data cleaning, the main task is data cleaning, and it's a bottleneck. So if we focus on the relation between CORES and AI, so on the one side you have CORES. So CORES is based on standard of W3C standard, and it's aimed to interconnect data in the web of data. So you have a language SparkQL to make some query, and you have graph database, and this graph database can be an input of some machine learning or deep learning or sometimes a computer vision, and it can go from AI to symbolic, because CORES is a symbolic approach. So with CORES, you give some semantic to this cluster. This is the idea. CORES give you some semantic, and with machine learning, you basically don't have a semantic. You have clustering or classifying, but no semantic. And well, I put here all the graph database ecosystem. I'll not go into details. And then I took this slide from Abel Samot, the French guys. It was open source, global open source AI mapping. So you have Mistral AI, GameFace, about LLM developer. You can you can see most popular AI framework. You have PyTorch, Scikit-learn, Keras, OpenCV, TensorFlow, and Spark. And here is to focus on Spark ecosystem. So you have different storage and infrastructure. I think maybe everybody knows all these technologies. Parquet is is a very efficient storage format. Elasticsearch, MongoDB, Cassandra, and for data science and machine learning. So Spark can interact with all these technologies. I think everybody knows on open source HPC accelerator. So Open Accelerator is a programming standard for parallel computing. One issue is KJ. The time. No. What you say? When is the time to build? Yes. I will make an iteration later because I only see the message and after it disappears. So you said when people say that the time is very costly of time to construct a knowledge graph. So you have compute unified, you have CUDA, you have OpenCL, and you have Sync, and you have AMD, and of course you can construct open source hybrid system, and this is an example with MPI model and with Open MP model. So I'm going to make a focus on Scikit-learn now. And after, on the conclusion, we will go more into details about different risks and what technology we could put with this risk. So what I'd like to highlight here is that all these technologies that is on madefirstmark.com. So it's a landscape about machine learning, AI, and data. So all of these technologies have a brick of Scikit-learn. So this is Scikit-learn is the most popular brick in machine learning, and you can load at this site. KG is a knowledge graph. Karim. KG stands for knowledge graph. I will make an answer to the question later. And okay, so in terms of some number, you have 1.5 billion cumulative downloads for 3 million of data scientists. It's a public and private open source community because first it was initiated by INRIA, but after you have INRIA Foundation with other partners, and it's open source community with different contributors. But you have INRIA core contributors and 2,000 contributors who are the user. And Scikit-learn implements around 160 models. And its goal is to democratize machine learning. And as you see, it's in a cumulative way. You have the same number of dependencies, PyTorch and TensorFlow, in perspective of Scikit-learn. The problem of TensorFlow is that it needs GPU. But if you want deep learning, it could be the case. But what I like to emphasize is that all this model are treated with Scikit-learn. So linear logistic regression is the most algorithm used. And this is a slide of Gaël Varocco, who is a director of research of INRIA. And what you see is that Bayesian approach and Gaussian boosting machine and decision trees or random forest, they are treated by Scikit-learn, who is very frugal and less consuming energies and compared to a network, a neural network. So if you want deep learning, it can be the case if you lead with image. If you have, what about generative AI and LLM? Generative AI and LLM are, you can have scikit-learn in LLM models, but here is only a focus about scikit-learn. So you in LLM models, you can use deep learning and machine learning, because machine learning can be used also to prepare the data. So machine learning is, LLM is very high cost model indeed. So for LLM, of course, you will use deep learning. It's preferable to use deep learning. If you have HPC and if it is non-sensitive data. Do you know this methodology? Well, this methodology is very nice because it's the algorithm cheat sheet of scikit-learn. So it guides you around to select the best model. So you can make lots of computation to select the best model, but before doing computation and coding, it's cart, a landscape to guide you. You have to take one or another algorithm. So this is very nice for a data scientist. And well, here we have the figure from the reference site actuai.com, which list among other things startup, and for each startup they have counted the number of startups with algorithm type. So most of the startups use ANN, probabilistic model, time series. And as you see, scikit-learn can address all this, much of this problem. And what we put later, we will, okay. And here, what we put also is you have cores for constructing a Newlands graph, and COC. COC is a formal, as you see, COC is a formal proof management system, and it's used for to certify some system. It's used in CompCert, for instance, certified compiler, and it is used in blockchain also. So all these are INRIA technologies. I can give you the reference. And all these technologies can be used with scikit-learn and its ecosystem and distributed on HPC with other open source ecosystem. And well, practical example, this is only to see the API. An example to see the API. Oh. So it's our feature. COC INRIA. No, because you forgot the E. You put But no, can't see. Not this one. Attends, hop, hop. INRIA. COC.INRIA.fr. Do you have it? COP, no, it's a Q. It's not a P. I give you the link. Voila, exactly. I give you the link. And COC can be distributed also, no problem. So, typical example. So let's take a feature or matrix X is only to understand the API, and you have a target, the class to predict. You can use, you can deal with visualize the distribution of a quantitative variable. You can delete redundant feature with this manner, and with Seaborn, you can see some correlation before doing machine learning. And with tabular data exploration, you can have an idea of decision tree concept. And after, you have to make some data splitting with train test split. Excuse me. And so our data set is going to be split in two parts. One part is the train set, and the other part is the test set. And after, in Scikit-learn, we use fit and score to evaluate the prediction. So this is an example of code. And what is good in Scikit-learn is it's a unified API. So you have different algorithms, but same API. So all of these algorithms use fit to train the model, score to make the score of the accuracy of the model, and predict to make prediction. So you can have linear, decision tree, random forest, bagging methods, KNN, support vector machine, and sometimes you have in Scikit-learn, you have multi-perceptron. It's a neural network, but it's better to use TensorFlow or PyTorch if you want to deal with neural network and deep learning. So this is an example of code: feed, score, predict. You have the same, exactly the same line of code. If it's linear regression or if it's decision trees. And do you will share the presentation? Yes, I can do it. And well, well, I'm sorry. So for the conclusion, we can we can make was that PC used in with attends, I will answer to the question later. So the error impacts regarding activity branch, it depends of the risk. If there is an operational risk, marketing or it's limited, but you have a ROA impact. But for autonomous vehicle, of course, mistake can kill. So, and you have operational logic, better positive or false detection or miss. So you can use, as you know, confusion matrix. And if you use confusion matrix, you have to use a metric to calculate what is the risk. if you want to make a classification. And also the choice of the metrics and has an impact on error, because mean square error penalize large error much more than mean average error. And so it will impact on this model, for instance. And here you have AI bias and technologies proposals. So you have you can have bias in data. Bias can be cultural, historical, aggregational, and temporal. So for this, you can use Scrub for prepping the data, imbalance learn for deal with imbalance data. You can use Cores to build some knowledge graph, even if it's indeed costly. So to unbias the data, you can use these three technologies. And in terms of algorithm, you can use hazardous Verlaine. So I remember for you that hazardous is analyzing risk. Verlaine is monitoring and mitigating responsible AI and HPC. And for the AI Act, I had an idea to, so you have four different risks: minimal, limited, and high and inaccessible risk. I propose to put some different technologies. So as you see, Cores and COC is in symbolic logic approach. And you can put Scikit-learn and all this is ecosystem. You can put Cores and all this ecosystem, and COC with all this ecosystem, and HPC with all this ecosystem, with to deal with high risk. Limited risk, you don't need COC, and minimal risk, you only need Scikit-learn, or if you want, you can use deep learning technologies. So I think we have a lot of time now to take a question, and if you have some question, I'm going to go to the chat and stop sharing my screen. So, what is your question? So Andres, my response here, it was only to make in a nutshell a global vision of open source ecosystem, Scikit-learn and HPC and Cores. So with I was the next speaker, they will develop on computation and details. Yes, it's Sebastian Muraro. It's the Scikit-learn is quite large. Yes, exactly. And there was a yes, Gérard Chollet, one issue with knowledge graph is the time take it to build them, but with HPC you can go much more faster with parallel calculation. Do you have some question? Other question?
There is one more in the chat, Laura.
regarding using AI to prevent breakdowns. Diagnostic component like SMART. Well, I don't know SMART. I don't know these technologies, but I know you can use a symbolic approach like PetriNet. But I don't have today's open source the open source ecosystem on a PetriNet. But you can use PetriNet with combination of machine learning and deep learning. But I don't like I don't know I don't have knowledge about SMART. Okay.
Hello, there are any more questions? If not, we can move on.
Yes, exactly.
Okay. Thank you, Laure. My name is Dragoș Baru. I'm the NCC coordinator in Romania, and I want to welcome you back to our panel session on AI and HPC use cases. In this session, we will explore how cutting-edge technology are solving complex problems and driving some transformative change across different fields. Our panelists represent the National Competence Centre across Europe and will share their case studies that combines the power of AI and HPC to tackle real-world challenges. First, we have Sebastian Moraru, a final year PhD student and full-time software developer in the AI department at ACI Bucharest. He has a dual expertise, including his work in international drug development teams. And Sebastian will take us to a journey into the tumor and microenvironment. His presentation will show how AI is opening new avenues in cancer research. So please join me in welcoming Sebastian to begin the session.
Hi, can you hear me? Can you confirm that?
Yeah.
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 I'll quickly share my screen. Okay. Just going to present. Just a moment. Yeah. So you can see the presentation?
Yeah.
Okay. So hi everyone. Really happy to be here and really happy to see that the number of people attending is quite large and much larger than I expected, honestly. And I saw everybody comes from a different country. I saw people from different countries, so that's quite beautiful. I think I come from an academia background, let's say mostly, and interconnectedness and collaboration and working together and sharing ideas. That's always something useful and something that I'm quite enthusiastic about. So my presentation today is about tumor microenvironments. I called it an initial sneak peek by making use of state-of-the-art AI tools. I've been holding some presentations on AI with some different occasions this year. And besides the usual question on whether AI is going to replace jobs and such, I think having cases that show where AI is really useful to enlarge our capabilities or literally help us either as assistants or as tools that are able to be used as mathematical analysis tools. It's really useful, I think. And I usually still talk about intuition whenever I give a presentation. So there is a cat on this first slide, and I'll just quickly say the story of it. So there was the Titanic, and there was a cat on board before the last stop. And the cat had a few kittens, but at the very last stop, before the biggest leg of the journey, the cat simply got out of the boat. And the people that were taking care of it and its kittens, the people from the kitchen mostly, they thought something is wrong, and they stepped out as well. And that's the reason why they lived to tell the story, that they followed the intuition of a small cat, and they were able to survive. That's still a question that is always on my mind whenever I work with AI. Okay, how much should somebody respect their intuition or develop their intuition? How much should somebody, well, respect the mathematics and develop AI tools? Right now, this presentation provides an introductory, an introduction into cancer microenvironments. Mostly it is statistically thought that cancer cases will grow, not only in Europe, but worldwide. I think a lot of the attention is towards the diet side. So people expect that many cancers will appear because diets became poorer in terms of quality. And you do have a few examples on this slide about survivability. So once you get diagnosed, what is the survivability rate in the following 5 years? And even if some of the cancers that you most commonly hear about, they could have, or they might have statistically a high survivability rate, you also have cases such as lung cancer, where once you get diagnosed, the 5-year survival rate is very, very low. So you get to 15%, up to 20%. Those are really low. So 1 in 5 survives 5 years after diagnosis. Usually, and this has been, the area where I've been paying some attention, in particular, head and neck cancers also have a very low survivability rate once you get diagnosed. And they tend to reappear very fast. So if you followed a cure of, let's say, chemotherapy, the probability for head and neck cancers to come back after a year, or for the patient to be re-diagnosed, is very, very high. And the question is why in some cancer cases, people find themselves re-diagnosed with cancer many times with a much more aggressive case of cancer, so more aggressive than the first one that got cured. If you go to the textbook cancer model, and this is, I think 10 years ago, I was learning about cancer as a student. It was mostly presented as a multi-hit model. So what is a multi-hit model? You would need multiple mutations from a healthy cell. You would need multiple mutations for it to become cancerous. So you would look at certain characteristics that a tumor cell has, such as angiogenesis, which means creating blood vessels around it so that it has a lot of, let's say, fuel, right? You resist, as a tumor cell resists cell death. A tumor cell mimics the receptors on its surface so that it is not identified by the immune system, and it mimics the signature, the receptors of a healthy cell, so that when a immune system cell comes to check it, and it's still not very large, it just looks like a normal healthy cell. In the meantime, going from the multi-hit cancer model, which required multiple mutations for it to become cancer, this field has exploded into many diagnostic, let's say, new ways to diagnose somebody, especially if we talk about early detection. And you got from 6 to 7 hits necessary. You got to the 2-hit theory of cancer causation. You got 1-hit So there are certain mutations that are really, really dangerous. And you also have certain scenarios, such as chromotripsis, which is still being investigated with a lot of interest, because you have the you have the chromosomes that simply are broken apart by some event, and they reassemble, but they do so in an erroneous manner. So they reassemble in a manner that has a lot of mutations and a lot of wrong junctions, and it's quite an aggressive way of getting to cancer. Nowadays, sequencing technologies allow you to generate a lot of data. So if we talk about cancer, online public data is huge. Whether we talk about, for example, bulk RNA sequencing, which takes in, for example, a blood probe and sequences it and takes it through some algorithms to put together the RNA, or maybe, if you'd like, the DNA of somebody, of a person. Whether we talk about that when we think about bulk, or we talk about the, let's say, newer technologies such as single cell sequencing. So what this does, it allows one to, using a laser beam, to separate cells almost individually. They are tagged with a certain barcode, and you can identify, let's say, 2,000, 3,000, I think newer protocols go up to 6,000 genes inside the cell when they are active. And you can sequence them and create and check the data, right, and generate a lot of data from, let's say, a blood sample. One of the reasons why this got a lot of attention is because there are many, many protocols when it comes to single cell sequencing. There is also ATAC-seq, which has something to do with the chromatin and the way that some genes are active or inactive due to chromatin arrangements. There is also CITE-seq, which allows one to sequence, besides the RNA inside the cell, also the receptors on its surface, to look maybe at the way that the cancer cell would hide itself and present itself as a healthy cell to the immune system's cells. So there is a lot of technologies that make use of this single cell paradigm. And all these technologies generate a lot of data. And how would you analyze that? Well, this is a point where AI comes really useful, and the point where HPCs are most of the times needed if you want to go towards personalized medicine, or hope that at the public level one day personalized medicine becomes more common, and that means a lot of data has to be processed. So looking at tumor microenvironments, one needs a better understanding of the components in tumors and their interactions. So that is critical when you design new treatments, and could aid, and definitely aids, in clinical management of cancer patients, because cancer is a complex disease where both tumor and non-tumor cells play critical roles in disease progressions. One of the, I think, more complicated cases is colorectal cancer. When you analyze colorectal cancer, you also have to look at the whole microbiome, including viriome and so on, and analyze the tumor as well, because when we talk about tumor microenvironments, I think somewhat recently there was a paper, but there is investigation. There's a lot of investigations now on whether microbes, when we talk about tumors, they live around the tumors, but also intratumorally, so inside the tumor. And that is quite an active area of research, and one of the areas on the spectrum that I'm looking at. So despite current scientific progress, it remained an open challenge to identify which microbial taxa reside intracellularly, and whether they reside exclusively or preferentially inside the tumor cell, or whether they belong to the non-cancerous tissue. How do they get inside the tumor cell, and what kind of impact they play over there in the disease progression. Why is this important? Because today we talk about technologies that allow for cancer cell reprogramming. So there are plenty of studies and active consortia, including in Europe, that work in reprogramming cancer cells using, for example, transcription factors, and either look for small molecules that would replace those transcription factors so that they would become medication, or there are simply investigations on what kind of transcription factors can push a certain tumoral cell in a cell culture and push it towards being a stem cell again. This is possible. I think I can give you an example where, using a combination of three transcription factors, you can push certain cancer cells back to a stem cell state in about 9 days. So I think this gets a lot of attention right now, because this could be the foundation of future cancer therapies. Whenever we talk about AI, for example, we can look into AI transformers. So if you use Hugging Face, PyTorch, I think I could thank one of my senior supervisors, Mr. Liviu Badea here, because he taught me quite a bit about the transformers. Whenever you apply transformers, for example, and artificial intelligence to genetic data, you will look at the embeddings. So I think the most popular embeddings are UCE, the Universal Cell Embedding Model, and GeneFormer embedding model. Now, there might be plenty that are more popular. I think for those of you that are familiar with BERT and GPT, there's also single cell BERT, there's also single cell GPT. So there's plenty of architectures that have been applied to single cell data, and they can be investigated. And you can generate inference, or you can investigate inference on your own computer usually, but you will still need a lot of VRAM. But if you want to fine-tune or pre-train something on genomic data, I think you should know that data sets are huge. So we talk about hundreds of gigabytes, or sometimes thousands, if you want to take this towards the clinical aspects, clinical investigations. So there are multiple models. I did not go very much in the details with this presentation, also because many of my results are still cooking in the background on HPCs. But many times you take, as in language, you can take certain architectures and you need to pre-train it on a big corpus, and then you can fine-tune it on a certain smaller corpus that is more specific to a certain scenario. In this case, there are tools that were made to help you identify microbes from tumors. For example, CSI microbes. This takes in, for those that are somewhat familiar with bioinformatics files, it takes in the FASTQ files or the FASTA files. So it is before you take the single cell files, which would be the LUM or the HDF5. So you take in the FASTQ files and you try to find in between your human genetic data, you should be able to find, if we're talking about tumor microbes, you should be able to find certain reads that can be aligned to microbial taxa. For example, one of the databases that I have used is Green Genes. And for those of you that are familiar with sequencing technologies, this only uses 16S rRNA. So it would only be for bacteria. But bacteria is also interesting alone, besides fungi and archaea or otherwise. Bacteria is also quite interesting because it is, and there have been studies that found short short chain fatty acids that play a significant part in tumor progression. And one of the questions is whether these short chain fatty acids play a huge role in tumor subpopulations that become very, very aggressive with time. So you have scenarios in which the main tumor, the one that grows very large, is actually keeping in check much smaller tumors, much smaller subpopulations that once the bigger tumor is removed or treated, the smaller subpopulations that are much more aggressive, they start to grow because the first tumor was actually keeping the resources away from these. So there was some sort of a balance. And once you take certain medication, you mostly treat the bigger tumor, the main one that you see. You become happy that you see a result, and then slowly you find out that smaller populations start to grow. And it is believed that in some scenarios, it is certain microbes that play a role in that. Okay. Besides, there is also a tool such as single-cell RNA box that also helps you with finding microbes inside tumor data sets. So what I did was focus on certain cancers. In this case, neuroglioblastoma. It's one of the cancer that grows very slowly, but if you once you get to identify it, usually that does not happen at an early stage, and once you get to identify it, it's usually at the late stage. So it would be very useful if for the future we are able to find very early biomarkers for cases such as neuroglioblastoma, for lung cancer, for colorectal cancers, neuroendocrine, prostate, and of course breast cancer. So going into these with the tools, I was able to build intratumoral microbiomes datasets. And of course, I promise I will send some of the results to Andrea, and she can forward it to the rest of the people. Once you generate those data sets and you are able to pre-train some of your architectures of interest, such as GeneFormer in my case, on microbial data sets, one can look and try to predict or estimate resistance to immunotherapy, tumor mutational burden, or heterogeneity of tumor antigens. In my case, I trained, or it is training, a certain architecture on microbial proteins that are supposedly promiscuous and bind to different tumor cell receptors. In that sense, this should say which microbes interact most with certain tumors. Yeah, and my results are cooking. I promise to be sending something to Andrea so that she can forward it to the rest of you. And thank you for your attention. I think this presents a case where HPCs are very useful because these things require quite a lot of computational power. So, yeah, thank you.
Thank you, Sebastian. We'll have a Q&A session at the end of this panel. So now I will hear from Monica Rotula. It's a PhD and machine learning advisor at SURF, representing NCC Netherlands. She will present the use of pre-trained large language models in the medical field, focusing on their application in assisting cancer diagnosis through digital pathology. This innovative approach exemplifies how AI is revolutionizing the healthcare diagnostics. So, Monica, you have the floor.
Thank you. Let me share my screen. I have to do some stuff in the system settings. Yes, okay. I have to go out of Chrome. Let me just export it to Chrome so it's easier.
Anything we can help, Monica?
Because I have to close Chrome, but I think now, yeah. Okay, now I can see. Let me see. Can you see the screen?
Yes, it's running. Yes, we can see your presentation.
Okay. Yeah. So, yeah, okay. I can do this if it's, yeah, because I had to restart the Chrome. That means that I have to go out and restart my laptop. Okay, so thank you for having me. I'm Monica Rotulo from SURF. I am actually a machine learning advisor, also as a main point of reference for EUROCC Netherlands. I have actually a background in engineer, but yeah, I didn't know that Sebastiano was already talking about cancer, but I thought that the medical application is quite interesting for us as well. Can you still see my screen?
Yes, we can see.
Okay. So yes, I'm gonna talk about using pre-trained large language models to assist cancer diagnosis in digital pathologies. And we start from what is digital pathology. So digital pathology is a workflow that starts in the lab, in the hospital, where samples from the patients are like collected and are like pre-processed to generate a gigapixel image of the tissue that you can see here in the picture. And this image is like wide and will be displayed later on a big screen where the specialists need to go pixel by pixel to understand if there are some parts of the tissue that are like dangerous, cancerogenous, or need further evaluation. And as you can see, this is not a process that is like 0 or 1, so either cancer or not, but is like involve the different stages of the mutation. And actually, the middle part, hyperplasia and dysplasia, are actually quite hard to detect for a specialist because you are like kind of in the middle of something that has a mutation, but you don't know still if it's benign or is already developing into cancer. But it's actually is there where we really want the practitioner to understand if it's something that we should really focus on. So at the end of this workflow, we have the histopathology data, which is indeed a pair of image and text. So the image has been pre-processed in this gigapixel final image of the entire tissue sample. And then is like next to it, we will have a report that has been generated by the specialist describing what has been seen in this image and if there is a sign of cancer or not. And how machine learning is currently used in this workflow? Well, it's we don't use the text report, but we are quite, let's say, advanced in image analysis because computer vision is already quite established. So we can already use image segmentation, for example, to understand if there are parts of tissue that requires further assistance from the technicians or the practitioners, but also for multi-class classification. So starting from an image, whether we can classify, we can assign first labels, and we can classify this image as a normal tissue or finally the later stage, which is adenocarcinoma. As you can see, we got rid of the previous text image pair. We are only using the image part, but actually this field is always evolving, and also machine learning is evolving, is actually evolved quite a lot since like the introduction of ChatGPT and large language models. So the idea is that instead of using the model to generate an output that is commonly hard to understand for the specialists and the doctors in general, can we use the power of large language models that can be now trained in HPC facilities to produce an output in which is in a conversational English or medical format, which is in a format that is friendlier to the doctor. So this is the premise of our work. So we start looking at our data, and we have indeed this data pair that is a pair of these gigapixel images, which are called the whole slide images and captions. And we actually collaborated with 2 labs from 2 different countries, because this project was funded by European Union, and it was like having partners from different European countries. And in particular, we could collect around 6,000 pair of this image and text, where we reserved a small subset for testing. Before giving this image text pair to the model, we actually needed a little bit of data processing, because we noticed, first of all, these 2 reports, for example, are coming from 2 different labs, which are speaking different languages. One is Dutch and one is Italian. So first step that we did is to machine translate these 2 different languages into a common ground, which is English. Then we also noticed that the captions, the report generated from the Dutch medical school were kind of like more providing more information, but this information were not integral to the diagnosis. They were like more messy, more filled with irrelevant and noisy information, while the data set of Catania, which is the other lab in Italy, was much cleaner and also in a more standardized form. So we use ChatGPT, and actually the previous version of the GPT-4, which was GPT 3.5 Turbo, to first clean the original captions that are already translated in English in a form that is without irrelevant information. And then we provided to ChatGPT some prompts where we showed these are the captions that where we really like the structure. Please like convert these other captions that are badly written in this format. So in this way, we could generate new captions that are like in a better format for our purposes. And here in this table, we can see that it actually managed to do a pretty good job, except the last one where he failed to generate the caption. Then after having this data in a more appropriate format and standardized format, we can go to the model development, which in our case involved a training phase and then a generation phase. Please stop me or ask any question if I'm going too fast. For the training phase, we first need to choose an encoder architecture to convert our modalities. In this case, we are talking about text data and image data into an appropriate format that is easy to digest for the machine learning model. In this case, for machine learning, we are always working in the domains of numbers. So we would like to generate a numerical representation, which is vectors. In our case, we chose these 2 encoder models, one for the text data, which is called the PubMed-BERT, which is a variant of the BERT model specialized in text data for the medical use. So it's a model that can understand medical terminology. For the case of image data, we use HIPT, which is a hierarchical transformer model that is built on purpose for large medical images. So it usually works that it can process and save into memory these big images that we are talking about dimension of 4,000 by 4,000 pixels. So what we want to do is, as I said, have as a final like a vector representation starting from these different modalities. So to do this, to achieve this, we train a model that is a clip and is actually coming from OpenAI to learn similar image and text embedding. Why we are doing this? Because in principle, we would like to have a similar vector representation starting from similar objects. Are you any of you familiar with the clip model? I can also, since I got some previous question in previous meetings, I would like to explain a little bit more because I understand the complexity of this step. And there are some keywords, like this sentence is really full of keywords. Like specifically, I would like to focus on the sentence, align similar image and text embeddings. What does it mean? So we start from the keyword embeddings. As already Sebastiano mentioned, in the machine learning, we represent an object with numbers. Therefore, we would have a vector representation. This means that before passing our data to the model for a downstream task that, for example, in our case is generate new text, we would like to convert our different modalities, so text, audio, images, into an appropriate format that is readable, digestible from the machine learning model. So as you can see, you have different objects and then you have a vector representation. So it's a series of numbers, and how big is this vector depends also on the resolution of this conversion. So more details you want to incorporate to describe this object, the longer will be this vector. What we mean by similar, like how we can say that two vectors are similar. In the math world of numbers, we measure similarity by measuring the distance between vectors. So what we do is that when we have clear sentences that are similar to each other, for example, in this example, we have the cat is on the mat, but also another sentence, which is the cat is sitting on the map. We, as humans, we know that these sentences are really similar to each other because our brain can process this information. But in the mathematical world, we would like to have vectors that are close to each other. So we would expect the distance between these two vectors to be very low. In the contrary, when you have dissimilar sentences that are really not related to each other, we would like to as well have vectors that are far from each other. So this is how we measure distance and have the concept of similarity in math and in the vector world. Finally, in our previous model, we talked about training a model to align similar embeddings. This is because we don't have these vector representations yet. We want to generate them. So before training, we could assign these images and text to random vectors in this vector space, as you can see from the image. But also, for our purposes, we would like to indeed enhance this similarity between a sentence that, for example, describes a red cat and also an image that represents a cat and is red. So we wanted to apply this case also to histopathology data, so that when we see an image of a tissue from our training set that has been described by the medical doctor as a tissue affected by cancer, we would like to give a vector representation that is close enough to a text vector that represents a sentence describing cancer. Okay, so that we would encode this information into the math world. The final goal is to generate new sentences. Given that our language model, we ask to generate new text while being influenced by the image. So in that sense, we can say that the image embeddings provides information to the language model. So if we pass to the model an image that contains cancer, we would like the model to generate a sentence that provides cancer on it. And this is a generative model, meaning that first we train this on some controlled data set where we know, okay, this is the image with cancer. Let's see if you generate correctly a sentence containing cancer. But then we would like it to also generalize from there. So when we give a new data, which is not being assessed by a specialist yet, can you already tell me in a sentence what I should expect? Something in this sense. Indeed, going further in the generation phase, now we have trained our clip model such that the encoder produce correct vector representations starting from images. And we know that these vectors are like spatially located close enough to words, potentially words, that represent the same concept. So what we do in the step 2 of this generation phase is that we physically connect this encoder to a pre-trained GPT model. In this case, is a bio GPT. So that means that it's already specialized on medical data, such that the model can see the image embeddings while it's generating the caption. And by seeing, we mean we achieve this by a term called cross-attention, which I will not go into detail, but it's basically a sequence of linear algebra operations and vector multiplication, such that to enable the GPT model to focus on the image embeddings while writing the caption. And indeed, the step 3 is generating the caption. So starting from a new image, assuming an image with cancer, this is first embedded into a vector representation, then it's passed to the model, to the decoder block of the model, that, for example, here we gave as an input, this image contain lesions of this form, and we would expect the model to finish the sentence. Since we gave an image with cancer, the GPT model is kind of influenced by this image, and it generates the sentence writing cancer, high grade. So this is the purpose, and also like the final scope. The final scope is having in place this architecture that given has been trained on a finite set of medical data that has been already assessed by the specialist. And when a new image is coming, is also able to kind of suggest what would be the expected outcome. And I would like to finish this presentation that I hope is clear with some final consideration. First of all, you can see the real caption versus the generated caption when we did the evaluation and testing phase. And we are very happy to see that we kind of reached a level of accuracy that is comparable of a supervised learning, where also the sentences are kind of accurate and they look like generated by a doctor. In this, I want disclaimer, with this work, we don't want to substitute the job of a doctor, but it's more of providing a support, because as I said before, the final reports are very highly subjective to the specialist. Indeed, we noticed that the Hospital of Italy was more let's say, precautious. So whenever there was an image a bit suspicious, it was labeling as cancer. While, for example, the Rabound University in the Netherlands was more calm about it, relaxed, like, so then it's like, okay, this doesn't require further investigation. So exploring machine learning and large language models for doctoral fields, medical field, we aim to help the practitioners to have a sort of tool to do double check, second way of verification. And I must say also another consideration is that pre-processing the data with ChatGPT was actually very helpful, because this enabled us to standardize the data set coming from 2 different labs. And finally, also a big thanks for HPC resources, because all of this pipeline, despite using large transformer models and large image that also don't fit in a normal memory, we were able to fine-tune our pipeline on a single GPU in just around 20 minutes. So this also is very useful because it enables us to do very quick testing and repeat experiments to improve our results. So I also leave some, oh, I have a question. Did you have to, no. So for training the model here, we just use PyTorch, and then we imported trainings, we imported pre-trained models either from Hugging Face or from OpenAI. But the only software that I can say that we needed to install on HPC was actually a visualization software, so that we could visualize these medical images. But for the rest, like this was the models itself was all programmed into PyTorch, and the difficulty mainly was to spread the trainings into multiple GPUs. Does this reply to your question, Andrew? So if it's not, yes, okay, yes, thank you. So I leave also some final references and resources. For example, the main paper of this study, which is as the first author, my colleagues, Brian. He did an immense work, and he was mostly the person in contact also with the specialist. I also some links and also for more resources to learn more about histopathology, and also the project itself, that is Hexamode, which is indeed an European project to use HPC and AI to help especially computational pathology group. And then final, some credits to my team, because I didn't do this work alone. Brian, Robert Jan, and Damian, they were quite involved talking with the scientists, having meetings, and dealing also with the technical problems, because the main challenge actually was also pre-processing these big images, because they couldn't fit in the CPU, so they had to be chunked into multiple pieces and saved into different CPU. So yeah, that's my presentation. If you have any question, I'm here to answer. I don't know if we have time. Thank you.
Yeah, we will have a Q&A session at the end of the panel.
Sure. Thanks.
Thank
I stopped
you,
the video.
Thank you. And now from NCC Spain at Chesga, we are joined by Laura Martinez Calvo, a PhD and industry champion, who will shed light on the use of AI for satellite-based surface wind correction. Her presentation will offer insights into how AI is enhancing the analysis of environmental data, with implication for fields like meteorology and renewable energy. So, Laura?
Hi, everyone. Can you hear me correctly?
Yes, we can hear you.
Perfect. And can you see my screen?
Yes, we can see your presentation.
Okay. So, well, hello, good morning, everyone. My name is Laura Martinez. I'm working as a project officer at CESGA. I have a background in life sciences. Actually, I was working in cancer for, I would say, my entire PhD and then 3 years afterwards. So the two previous speakers really remember me things from my past life, let's say. So it was a pleasure listening to your stories. And now we are changing a little bit of topic. I will present you our experience with the Spanish company Now Systems that they did with us an EUROCC Spain testbed. I'm just going to briefly introduce this initiative from NCC Spain. That is, this testbed is an open call, is continuously open during the duration of the project, so there are no deadlines. We designed this call with an easy and fast online application. You just have to write a one-page online form, and we are going to answer you in 2 weeks. So it's quite fast comparing to other calls. Initially, this was an initiative that we designed for the first phase of the project, and it was focused only in industry. So it was available only for Spanish SMEs and big companies. But this year, and given that the format was successful, we also opened it to academia and public administrations. And we are not currently developing 2 cases with them. And what are the characteristics? The main thing about this testbed is that it has to be applied for research and innovation activities. It has to be a quite small project, let's say like a proof of concept, a scalability study, some kind of testing, and it has to be done in less than 6 months. And finally, the resources that we are offering at no cost are up to 50K hours of HPC resources and also personalized consulting. So having said that, I'm going to talk a little bit of our partner in this experience. Now Systems is a Spanish big company dedicated to provide oceanographic operational services. What does that mean? They use and they provide applications, AI-based solutions for monitoring and forecasting everything related with the oceanic information. Their clients get tools that help them making decisions. And who could be their clients? They could be like portuary administrations, fisheries, transport companies. Also, they are working with emergency services. So let's say that their impact is quite broad in this sense. And I want to point out that in this experience, we are going to focus on a maritime area that is from the south of Ireland and all the Spanish coast, Portugal and Spanish coasts. So they are in charge of this area forecasting. And what was the challenge that they were defining for doing in our testbed call? It was focused on the correction of winds. They have currently a model that predicts and kind of forecasts the wind behavior in this area that I just talking about. And they were asking for our help in two things. The first one was the pre-processing of the SAR files. They have like a lot of images that come from the satellite, and they have to basically process them to turn them in a more longitude, latitude information. This is very simply put. The process is quite tricky, but I want to keep it simple, also because I'm not an expert in this area and I don't want to screw it. And the second part is they were asking for our resources for training an AI approach. They are currently using a dynamic model of winds, and they want to try several AI architectures to try to improve the results. And after several trial and errors, they decided that the optimal solution was the generative adversarial network. Basically, this architecture has two components. One is a generator and the other is a discriminator. So basically, and again, very simply put, they have real data from wind fields and all this information related to wind. That is our focus in this project. And they are going to generate data based on that training data that they have. And then they have to train another part of this, this network that is going to say and try to decide if the generated data is real or is fake. They go through several iterations, they set and tune several parameters. I'm sorry, I cannot give you a lot more information about this. And then they get the results. So they have the architecture going and well set. So the results here were really promising. You can see in the red square the AI approach that we are testing with in this project, and in the blue square one is the current existing dynamic model for winds. So as you can see in the QQ plot, in the current model that they are using, there is some deviation in the tails of the graphic. Let's say that the wind speed, that is the data that we are seeing in the x-axis, for lower or kind of for extreme wind speeds, like the current model doesn't behave very well. And with the new solution in the red square that we can see above, that behavior is improved. Moreover, given the dispersion to the diagonal, we can also see that the new model, the new approach, the IA approach works better. In fact, the correlation goes from 0.97 with the current model to 0.99 with the new model. And also the differences are reduced, like we are more accurate. We go from 0.57 to a 0.36. Other results, what they did was also, I was showing in the previous slide, data from the Northeast Atlantic, that is Galicia region. They also tested in a broader region, the one that I was talking beforehand, from the south of Ireland to the Canary Islands, and then to the Balear Islands, let's say. And they also tested it in case of extreme events. So there was a storm this day in November 2021, and they could see, if you see in the right-hand graph, the right-hand map, that the behavior is, broadly speaking, very well. It's very good. You can see there are some deviations in the island, the Canary Islands, but that's something to be expected, because when the model doesn't have like a big part of, let's say, land, it's really common to not work as well as in open sea regions. So about impacts and benefits, they were really pleased to know that applying both HPC and our GPUs in their processes really reduced the time that was needed to test this hypothesis. So, for example, the pre-processing they had to dedicate 20 days to do the pre-processing of the images from the satellite, and doing it in our infrastructure. That time was reduced to 2 days. So the time reduction was really impactful in their development. Also, the use of HPC resources versus on-premises, it allowed them to reduce the cost on development. they were talking about that they can now use their on-premises infrastructure for other things, not for this pre-processing that was so heavy and so limited in terms of a first step for doing everything else. And lastly, they managed to get their objective. They increased the resolution of the model and they decrease the errors that the current model is doing. So basically, this has impact not only on the wind prediction, but in all the models that they are working with, in which the wind prediction is an element. So as a plus result, they actually are trying to study this further. So they already got a new project, a new European project, and they want to test this new AI-based approach in a broader area, in areas outside, let's say, Europe, where maybe other meteorological events take place, like, for example, hurricanes or big storms, maybe in Asia and other regions. So they are thinking on implementing this new approach operationally by the end of 2028. So we are happy that our initiative, the EUROCC Spain testbed, helped them like set the first step in this new and big thing that they are going to do. Please do not hesitate to reach out if you want to know a little bit more about this success story. You can check that in our national webpage. If you can contact me, or if you want to contact with the company, just here's the email if you want to check out. And thank you for your attention.
Thank you, Laura. The next presentation should be from Andrei Deliu, EUROCC Austria. Is it here? I don't see it in the list. Anybody from NCC Austria? Seems that he's not here. I'm sorry for that. So I think we can move to the Q&A session of today. So everybody has some questions, or write it in the chat.
I sent an email to Andy, and I think that we can have the Q&A session, and maybe they will enter.
Yeah. Okay. If when it's back, please tell me. Okay. So we switch to the Q&A session, and if he will be here, we will invite him to present. If you have any questions for the presenters, please write it in the chat. Or any question, reflections, or anything. Even for Laura, for the introductory presentation on Scikit, on PyTorch, or any other questions. If not, I apologize again for Angie that is not here to present his work. I just want to thank you all for coming to today's workshop and engagement. Our workshop has reflected some question and reaffirming the collaborative spirit that defines this community, and in the light of AI factories that will
Sorry, Dragos.
Yeah.
Just a second, because Andrei just sent me a message, and he is coming. Just
okay.
Just wait some few minutes.
We'll wait a few minutes.
I'm there.
Hi, Angie. Nice to see you. Yeah,
Nice.
yeah. We are ahead of schedule, so welcome. And I will invite you to present. Angie Deliu is a fellow at EUROCC Austria. Has 15 years of experience as an AI consultant in Silicon Valley, and now focuses on helping Austrian startups strategize and develop AI application. He will talk about AI journey for organization and from inception to excellence. And we'll outline the path the organization can take to successfully integrate AI into their operation. So welcome, Andrew, and the floor is yours.
Thank you. Yeah, let me share quickly. Hopefully it works. The content. Screen. Can you see my screen? I hope so.
Yeah, but we don't see the presentation. Yeah.
Yeah, I'm moving.
Yeah, we can see it now.
Cool. Yeah. So I'll keep it short. The topic I cover is generally larger, but essentially today I'll talk a little bit about what do you need to excel in AI for real use cases. And there are two things actually that get missed out typically when we talk about AI. The first thing is infrastructure and operations. And the second thing is the product evolution. You don't get to become excellent on day one in both of these topics. Yeah, quickly about myself. I'm currently an AI startup angel and an AI advisor for a few startups in Austria, in Vienna specifically, and I'm an AI fellow with EUROCC and University of Vienna. Before I was actually a distinguished fellow with Indeed.com, one of the largest job websites in the world. I was one of the founding members of Einstein AI with Salesforce, also in Silicon Valley in San Francisco, and a principal architect for Sony PlayStation for recommendations. So my area has always been ranking and recommendations. And as part of my journey in some of the largest companies, I saw firsthand how important infrastructure and operations is, even before we even had a name for it. Typically right now, since a couple of years, it's called ML operations. So what is ML infrastructure and operations? I'll talk a little bit also where is the connection with HPC? Where does HPC fit? Because I mean, this is the topic of this entire workshop. So what is ML operations? ML operations is a set of processes and architectures, infrastructure and tools to ensure reproducible, scalable, robust, and observable ML lifecycle development and deployments in production. So there are two keywords here. This is a long definition, but essentially the first keyword is ML lifecycle. Everybody has to remember this when we talk about AI. What is the lifecycle? What are the stages that an AI model goes through? And then deployment and production. So these words, unfortunately, are seldom seen when people talk about AI. So I'll talk about a lot about these. So what does the ML and AI canonical lifecycle, the typical textbook lifecycle, look like? It typically involves several major stages. The first stage is anything that has to do with data transformations, data preparations, data engineering, and associated with each of these stages, even in this case, for example, we always have components that allow us to manage data at large scale. So this is the first and critical stage. The second stage, which is typically what people think of when we talk about AI, is training. Associated with training are multiple components, but one of the key components is training infrastructure, and then a repository of models. People call it model store, model repository, etc. This is the place where we track and version models. Then right after training, people don't talk about this a lot, is actually the validation phase or evaluation phase. Now, we always check how good is our model. Even in this phase, we need at the very least two things, test infrastructure and also a place to structure the configurations and results of our tests, of our evaluations. So this is currently in evolution in the AI ML infrastructure component landscape. There's not much out there. I'll talk about this. And then last but not least, there's deployment. So after we produce a model, we checked beforehand that it's good enough for us, we actually deploy. What does deployment mean? Deployment means we make it available. For what? Typically for inference. And one key thing that I'll talk about is the deployment is not like a simple thing. You push a button and you're done. No, it's much more complicated than that, and typically involves consultation with quality checks to actually alter the journey of the deployment. We have many different complex deployment types, and this is again one of the things that people don't think about, but it's actually critical for production deployments. So what do you need for an ML operational system? The first thing that you need is how do we express essentially its life cycle itself. Life cycles are complex. It's not always the same. Typically, we express them via flows or pipelines, workflows. Like that's the typical name. As part of like, this is a little bit more complex life cycle. I'm like in the previous slide, I had data, just one single stage, but it actually can be a lot more complicated than that. We can have multiple data sources. Then we have different stages, what we do with data. We have data cleaning, data augmentation, data encoding, and so on and so forth, data tests. So like that single circle that you saw before can be a complex graph with multiple steps in it. And so even the other stages can be much more complex. And we need a tool to actually express this in terms of code and in terms of systems. And that tool is called the orchestration lifecycle or workflow systems. There are two major paradigms that guide these workflow systems. And based on the paradigm, you can actually even categorize the available tools, open source tools that are out there. The one major paradigm that is visible, and it's actually an older paradigm, is called process-centric. This is where tools like Airflow, Argo, which is heavily used in the Kubernetes landscape, and so on. Like these are very popular tools for data processing and for ML. This is where they fit. So what is the key differentiator of this paradigm? The key differentiator is that these life cycle stages, so basically data transformation, training, evaluation, deployment, they are coupled with the computational process. So they are always, there is no distinction, right? Like about life cycle transition stages and the compute process, the compute cluster that performs them. In fact, Airflow is coupled. Airflow runs within the computational cluster, and there is no distinction, right? So there are benefits to do it this way, but there are big downsides as well. This is sort of state of the art, what's out there. And then there is a newer paradigm, which is called event-centric. So these newer paradigms are more appropriate for microservices orchestrations, and they're event-based. Event-based means they decouple, like they distinguish between where the lifecycle stages are managed versus where computation is happening. And by computation, I mean computation for data transformation, computation for training. So these are associated always with computational clusters. HPC plays a role here as well. But the key distinction here is the separation, the decoupling of these two things, right? Like lifecycle events versus compute. Where do we execute compute? At the end of the day, I'll explain a little bit why this is important, why these two paradigms distinguishing what tools provides what is important. It's important because the trend is to go to managing many specialized models, which are small, and they're specialized for a particular task. And that means, you know, managing many life cycles, eventually lots of them. It can go to tens of thousands, millions. If you have these numbers, these cardinalities, especially in shared infrastructure, then you have to be very careful about the choice of the workflow manager. Okay, another thing about lifecycle that I'd like to add is we also have this whole different world that HPC doesn't cover at all, which is called real-time inference, online inference. Here we also have a life cycle. It's typically the life cycle of the request. So if you get a prediction request for a particular model, it's not like a monolithic thing that you get an answer immediately, but there is quite a bit of sophistication inside in the systems that major AI tech companies have. I'm giving you a little bit of insight into what happens, for example, for a typical recommendation use case, a recommendation system. Here we have typically 2 major stages. Each stage is associated with one particular step or multiple. First stage is, in our recommendation case, candidate is what is called the candidate generation phase. Here, for example, typically there is a large vector store or large search engine that does a pre-filtering of billions of items to maybe a few millions. So this is the first filter. This is the first stage, and this provides you these few millions of appropriate candidates of items that may be relevant to a particular user. That's how recommendation use cases work. And then comes business rules. So out of these million items, not all fill certain business rules. Business rules may be anything that is lower than this price, etc. Right? So this is another stage of pre-filtering. And you go here again from billions to millions to maybe a few hundred thousands. Then there is as soon as you reach this phase of a few tens of thousands, you have 300,000 items, you can actually perform sophisticated and expensive ranking. Ranking is model-based, so there is a model behind this. And you go again, like this again, ranks and filters, gets the top X items, and the top X can be now, you go from 1,000, 100,000 to 1,000, or like so. And here, in the ranking phase, you can have multiple stages. Again, you can have 3, 4, 5 rankers that care about different things, are optimized on different metrics. And this is just to show how complicated inference can be, and that it also undergoes through a life cycle, through a step, a workflow of sorts. But this is all very fast, right? Like it has to happen within milliseconds, 10 milliseconds, right? Like you always have a time budget. So going back to that life cycle diagram that I showed, actually, so what is required? What's absolutely needed for production use, ML and AI use cases? So typically it's data systems. And data systems come in various flavors. They're geared for different use cases. Typically what we see in the big data space is data warehouses and data lakes. There is a different concept that has evolved now in the last couple of years called data lakehouse. But at the end of the day, they fulfill similar role. The role that they have is to, for data warehouses, for example, these stored large tables, curated data. So this is data that we trust. So trust is a big element. How trustful is data? How timely is it? Like in data warehouses, you can ensure that actually a table has a field, and that field gets filled relatively frequently, and you can trust it. Like you can trust its quality. And like under the hood, they're typically very large SQL type data that is either managed in the cloud or is on-premise, is built on-premise. But like the players here in the infrastructure field are things like AWS Redshift, plus Tableau. So data warehouses typically also have a visualization component associated with it. Tableau is a visualization tool. Or you have Google BigQuery. So these are cloud tools, but under the hood, actually, they are large distributed SQL databases. Then you have data lakes. Data lakes are a little bit more messy. They can store, I said for data warehouses, they're typically large tables, large SQL tables. So you have schemas, you have some notion of what the data is, what it represents. Data lakes are, you can think of it more as a dump, but it's a very large dump and it's very cheap. So that's sort of the distinction. Data lakes are typically cheaper than data warehouses, and they store both structured, as in table-like tabular data, but also unstructured images, logs, or semi-structured. Logs are semi-structured, and essentially what data lakes store are data of the entire company. Here you don't have a lot of quality guarantees, but you have guarantees as in you can find all the data of the entire company there. But in terms of adding that trust component, you have to do work yourself, as in you have to ensure that pipelines are built on top of these data lakes, and that the outcome of those pipelines are consistent, essentially. So pipelines run without errors, etc. So you have to do quite a bit of work to actually go from a data lake to an actual ML use case end to end. And then there is feature stores. Feature stores are essentially similar to data warehouses, but one of the key value adds for feature stores is that they don't just manage batch use cases, as in offline use cases, right? You're not dealing only with batch processes where you store and manage billions of records in batch pipelines, but here they need to also ensure consistency about online serving of features. Like that recommendation use case that I showed before, that's actually a very good use case for a feature store where a model, for example, needs clicks in the last 5 minutes, right? Like, so feature stores are the ones that provide that, and they provide that very fast. So they provide that for online use cases where they have to respond within milliseconds. They also provide it for offline use cases. And typically they are built on top of data warehouses. So it's like a layer on top of data warehouse. This is a chart. I'm not going to spend too much time here, but this is a chart, and this is very Azure centric. Azure is the cloud, the Microsoft cloud. What happens, like how these components are interconnected. Typically, you have a bunch of data sources that come from production systems. They may be SQL servers that are serving actually live traffic somewhere. They may be table storage, etc., etc. So these are the sources of data, and then there's typically pipelines that ingest these sources into a data lake or data warehouses. And then on top of that, there is, for analytics use cases, there is an analytics engine. These are typically systems like Athena, etc. Athena, Presto, Trino. So these are very typical for processing data in batch and providing analytics and visualizations. And there is a visualization tool as well. So that's the analytics path. There is an ML path as well that I'll explain a little later. So that was data, one of the stages in the life cycle. Then model inference systems or models in general, like how do we deal with models? This is the training part. So we need model training systems and infrastructure. And here the landscape is very diverse, very wide. Typically in large companies or even in smaller companies, you have managed Spark clusters, or you have Kubernetes, for example. K stands for Kubernetes. You have Ray. Cloud vendors have their own processing engines, and what they support is they have native support for distributed training, and by distributed training is meant things like classic models, right? Decision trees, boosted models, neural networks, smaller neural networks, specialized, and also larger models, and especially this intersection of large models and large data is where HPC plays a role. HPC fits here in this space, and this is where you sort of can categorize it. Unfortunately, HPC does not fit on the data part. It does not fit on the deployment part, etc. So it has a few major gaps to use it end to end. Then there is inference. HPC does not play a role in inference. There are major projects that are going on now for HPC centers to actually support inference as well. But inference is a critical thing, because at the end of the day, if you train a model somewhere, what good is it? Like, what do you do with it? Right? So where do you deploy it? How is it served? Like, all these other stages need to be covered for you to be successful, actually. So it's not just training. And then there is model stores. Model stores is essentially this place where you store the training output, the model files, model versions, model configurations, etc. And this plays quite a big role in actually inference. So in inference, typically the life cycle of the request, again, you have to respond within milliseconds. Typically, like the internal inference systems, the ones that are sophisticated enough, have to interact with a model repository or model store to figure out what's the right model version that I have to serve now for this request, for this customer, etc., etc. So this router is where most of the IP, intellectual property, resides. It's one of the most sophisticated pieces in inference systems. And then the router decides, okay, I go to this cluster that has this version of Scikit-learn or XGBoost or PyTorch or TensorFlow, or this version of Llama 4 or whatever. Llama 3, sorry. So yeah, these are sophisticated systems. HPC does not help you here. Okay, testing. Testing was that third stage in the AI lifecycle, in the ML lifecycle. Like, how do we ensure quality? Quality is very, very important. People don't talk enough about this, and it's why many AI projects fail, actually, because people focus on training, but actually the problems arise much later in production. So quality, you have to ensure quality is measured well and is measured consistently. Like the current situation in the industry is not very principled. Quality is measured typically ad hoc. Like you train a model, there is a data scientist or engineer that checks the metric, says, yep, good enough. Okay, we deploy. So it's very manual, right? Like, and it's metric centric. What needs to happen, it has started to happen in many larger tech companies. They are thinking about quality much more in terms of how we think about software quality. In classic software, we don't say metrics, right? Like, oh, what's a metric? No, you say you have a suite of tests, and you check behavioral scenarios, right? And behavioral scenarios have a clear pass-fail outcome, like a unit test, for example, and that tells you like how good is your model, right? Like, so essentially, we have to go from this metric-centric approach to a test-centric approach. And this is a major shift in paradigm and also in thinking. There are testing and metrics in AI. So again, they're associated with components, infrastructure components that support this process. Metrics, we've done metrics for a long time. Typically, they're calculated by SQL engines, Presto, Athena, Trino. These are SQL, large-scale SQL engines. They're supported as managed components in the clouds or on-premise. There are plenty of open source solutions here. Then there is OpenTSDB, which is a database. So these are for calculating metrics, and OpenTSDB plus Grafana is for storing and visualizing. There is a bunch of vendors, very new actually in the last 1 or 2 years, that is emerging. Like I can mention a few companies: Arise AI, Evidently AI. Most of them are in Silicon Valley. And what they offer is essentially something akin to an evaluation store. Like, how do you store consistently tests or evaluations, and how do you express them in an easy way? And so essentially, like, one of the things that need to be done here is build versus buy. Like, do you build your own or do you buy, right? Like for small companies, SMEs, typically the equation here falls on buying something ready, but buying gets expensive very quickly once you scale up. Okay, so another thing to consider with testing is testing has many dimensions. Typically, again, when you do naive AI ML development, you say, oh, accuracy, and that's it. But there's not just accuracy. So like accuracy can fit within performance type of evaluations, but you have things like robustness. Like, how robust is my model, right? Like, robustness means in the context of ML models and AI models is you perturb a little bit the inputs, and the expectation is that the outcome, the prediction shouldn't change. And if it changes significantly, it means it's not robust. What you have, privacy, you have to have privacy checks, like a suite of tests that checks for privacy, security. Right now, as we speak, actually, many larger companies are building red teams, internal red teams to check for quality. OpenAI, Anthropic, etc. Even for the larger, especially for the larger models who are very unsafe in terms of privacy and security, they actually have dedicated red teams, large red teams, and they have a suite of quality checks that they go through. And fairness and cost, right? Fairness means typically you test, let's say, even performance metrics for particular segments, because like a model can look good on a global level, global metric, but as soon as you go and peak within particular segments, let's say women under, like in your entire data set, you may have a segment that is called women 30 to 40 years old, right? Like, and your metrics may look completely skewed for that particular segment. And then cost, right? So my point here is testing AI is a whole different level of rigor that is required from what you typically see. And again, like, there is a suite of infrastructure components that helps you for this. Okay, now we come to the one of the most interesting stages, which is deployment, right? Deployment means, okay, I did all these things, I produced the model, etc. I have my data, and so on and so forth. What do I do with it? So typically, you want to deploy it to make it available somewhere for your end users to be used. And this deployment is not like an event. It's not like you push a button and it's done. No, it's typically it's a process. It's a long process. Why is it a process? Because it involves always quality checks. And I'm going to give you, so it's a process, it's a long process, and it involves like consultation with tests in terms of how the deployment of a particular model version is doing. And it also involves monitoring. So there are these two things, right? So one example of complicated deployment is a typical A/B test. A typical A/B test, like, well, life cycle of an A/B test is you have two different configurations for your model that are testing different things. Then you deploy A, you deploy B, version A and version B. let's say for 50% of the users, 50% gets A, 50% gets B. So this is a deployment process, right? And then, or you even deploy like the new version, the version that you just created, that was just finished against the old version. And then there's typically a check with the suite of tests that you have, right? Like, so the new version has to have accuracy between this and that. It has to be robust between this metric, and this threshold and this threshold, and so on and so forth. And then after a while, you decide, right? So there is a decision that says, okay, A is the winner or B is the winner. And this decision for A/B tests is typically manual, so there's a human doing it. But there are more sophisticated deployment types than an A/B test. A/B test is very simple. So you can conceptualize this picture here. So you have two versions, 50% one, 50% two. Then after some point in time, there's a decision where one version wins and get all 100% of the traffic. But then you may have, more than two versions. Number one, more than one check in point in time, and then even the decision how much traffic to route to a particular version can be much more granular. So you get a graph like this, where you have ABC, just three versions in this case, and then after set periods of time, you have this adjustment of the traffic that is routed to one particular model to cover actually most of the traffic, right? So this is called multi-arm bandits, etc. So instead of 3, you can have 5, 10, 15, etc. So the number is variable. But what's important here is that you do a gradual adjustment of the traffic towards particular versions, and then you go to like super sophisticated deployment types where you have this is just depicts 3 for the sake of understanding, but you may have thousands, tens of thousands. So this is contextual bandits. And the key distinction here is that you don't just have a single winner, but you may have thousands of winners, millions of winners. What does a winner mean? It means you have a model version that is serving just a subset of your users, of your customers, and that means you have many versions that are serving at the same time concurrently. So we're going from this very naive world of, oh, I have a model and I'm training and I'm deploying and I'm done, to this much more sophisticated, which is where reality is going right now for many companies, much more sophisticated version of, oh, I have actually in production millions of smaller models, and these millions of smaller models have their own life cycle, which, going back to that story that I told you about, how important it is to choose the right workflow manager. You have to keep the full picture in mind, right? Like, so what's the cardinality of models that I have to serve? How much control do I have over my entire system? So that's how you pick the workflow engine. So we're going towards this world of modular AI. Typically in software engineering, we have this concept of modularity. You seldom see it. We've moved away in software engineering since decades, actually, from so-called monoliths. In AI, that world, that transformation has not happened yet. Typically, we train these large models, and they're monolithic because we don't know how they actually make decisions. Inside, we have very little control over it. What's happening right now is it's a very interesting transition. We're going from these monolithic artifacts slowly but surely towards a much more modular and specialized world where you have composition of multiple models. Typically, most ML use cases have this feature actually of composing multiple models that are catered, specializing at a particular task, and they work together to achieve a final result. This is why essentially we will go more and more towards this world of managing many intelligent artifacts. I'm going to call them intelligent artifacts, not just models. Models are not the only thing that we have to care about for production machine learning. You can think of, I have this scale here where you can think of these artifacts as having some sort of intelligence. Prompts, for example, with LLM, prompts are, in a sense, intelligence, but the intelligence has been provided, is encoded by a human, and a prompt, contains a piece of knowledge, but it's not learned, right? So it's provided, like somebody gave it to you for free. Rules are similar, but are not expressed in natural language. They're also more precise, but they fill the same role. Essentially, they contain knowledge. They're also provided typically, right? Like then we go to this learned representations. And learned representations are learned actually. So here the human biases There are human biases here as well, but they are encoded as part of the optimization goal, etc. During the learning process. A typical example is embeddings. Then we have linear models. Linear models are full-blown models. The difference, one interesting difference with between models, representations, and prompts and rules is that for models you have essentially they contain two things that are explicit that define their functional behavior. They contain data, objective, and quality. So objective means what's the optimization target. When we train linear models or even more complex models, we always provide in machine learning training processes, loss function or optimization objective, right? Like, so that's what a model has. And you can manipulate it individually for a model. That's not the case for learned representations. And then quality, like what are the checks that you need to the tests that you have. That's also important for a model. And then models have their own scale, their own sort of spectrum. You go from very simple models to neural networks all the way to large models. But essentially, we have to see this as a spectrum. And the key distinction to make to enable modular AI is that most of these are actually small. So a prompt is very individual, expresses knowledge for a particular person, and it's very small, right? Like rules is the same. Embeddings are also small. It's just a vector. Linear models are also small, and so on and so forth. Like, so the future is essentially to have many of these and to compose, right? So we're seeing this more and more in the LLM space. They're called experts. Like there's a term for it, expert models, and like they are going towards decomposition and modularity as well internally. Okay, so moving on, 5 minutes so this was the infrastructure, very broad overview about what you have to care about infrastructure. You have to care about all those stages, not just training. And then now on the organizational side, like how does a journey of a company look like? I'm going to spend 5 minutes here. So first of all, there are many types of organizations and so on and so forth. I'll talk in general about what do you do, how do you start even, but also speak a little bit about the challenges of small and medium-sized organizations. First of all, you need some sort of an idea, plan of an AI data strategy. Like, so you need both AI and data. If you don't have data, you cannot do much. So where do you acquire data, and so on and so forth, like a technical strategy, but also organizational strategy. Like where do you get, how do you start? What are the first few critical hires, AI hires that you have to do? So first, there is a high-level decision from the CEO or CTO to actually go this journey. And then typically organizations go through 3 major phases. The first phase is the initial phase. I call it the POC phase, where essentially you identify sort of what are the key major use cases that we have within a company. And typically they fall within 2 buckets. The first bucket, if you have decent enough size of an organization, is improve internal efficiency. So this is, for example, where assistants are making a furore right now, because like you can have assistants for coding, assistants for your business managers, and so on and so forth. This is about improving internal efficiency. Then another one, more important one bucket, is when you use AI integrated into your products or processes in the company, right? Like this is where you AI actually earns money. It's not about saving, it's about earning new things, right? So these are the 2 buckets. But in this first phase, what matters is that you start actually. So you validate the key aspects of the AI value proposition for your company. So you find the 1 or 2 use cases that you think are valuable, and you start. And what you validate here is the go-to-market. And also another thing that you gain here is competence. Like you have to start somewhere to build competence internally, to build know-how. How do you deploy, how do you train, deploy, etc., manage models, manage AI, and how do you integrate them successfully into your product? This is the phase to do it. What you shouldn't do here is care too much about, revenue, right? Like, so you shouldn't care too much. You should have a little bit of leeway here to experiment, to try things out, not care too much about earning right away. So this phase can take from 3 to 6 months to a year, depending on the organization. Another thing that I'd like to mention is, because everybody is now, oh, LLM generative AI. So AI, when we talk about AI, AI is much broader. The typical use cases, we can, there's probably more than this, but there is things like planning, forecasting, recommendations, decision intelligence, autonomous systems, perception, intelligent automation, segmentation. All of that involves AI, typically classical AI models. Then you have anomaly detection. Then you have, these two bubbles here: content generation, assistance, code assistance, etc. This is where Gen AI plays a role. Knowledge discovery is also where Gen AI plays a role, right? So it's just two bubbles out of like 11 or 13. So when we talk about AI, we should be careful. It's not just Gen AI. Okay, phase 2. So that phase 1 is POC. You build your first team, first hires. You experiment a little bit with the use cases that you think are valuable for your company, and then you gain experience, you gain competence. The second phase is about scaling. So you scale both your team. So you go beyond that first couple of hires, and you scale the infrastructure, scaling infrastructure. So you go beyond pilots and you go towards particular flashy use cases. You serve everything, like you go and attack the major use cases in your organization, the money makers essentially. So this is the second phase. This is where most companies actually fail. They don't know how to do it because scaling is hard. Scaling infrastructure is hard. Number one, scaling organizations is hard, and it needs capital. One of the things that I see compared to Silicon Valley, to the US, right? Like what Europe misses actually is capital. It's not talent. So there are plenty of good people, plenty of know-how, but it doesn't know how to do this well. And why is because lack of capital. One survey, very recent survey from Capgemini about, this is particular to Gen AI, like what's the level of confidence of organizations to be able to scale generative AI. Proof of concepts is it's relatively low, I'd say. So like roughly 18 to 20% of the companies say we are aware and know how to production and monitor large language models for our use cases. It's the darker bars here. But then 70 to 80% actually are the ones that say, oh, we actually don't know. And we have trouble scaling the POCs. We have trouble going beyond the POCs. And most of the infrastructure is available right now, like the OpenAI APIs and so on and so forth. They help you with this phase, with the POC phase. It's very easy to get something together in the POC phase, like build, there are a bunch of components that you use, Llama Index, LangChain, etc. You put something together quickly, but then as soon as it is about scaling, it becomes hard. Because scaling is not just about the infrastructure, it's about also the processes. For example, like to give you a concrete example, how do you do customer support if you have a complex chain of LLMs? If an error happens and the error is shown to the user and the user reports that error, right? Like it tells you, oh, I have an error here, and so on and so forth. Then it goes to a person that goes and sees and tries to reproduce. So for LLMs, reproducing is very hard because it requires the entire context of the conversation, not just the last request, right? So it's very different from how we do support level 1 or level 2 or even level 3 support for normal software. Anyway, so and then phase 2, scaling team, scaling infrastructure, hard, not very easy, but it's again the phase where ideally you shouldn't worry too much about actually bringing in revenue. So this is the scale where you validate your entire go-to-market strategy and can we even scale or not, right? Like phase 3 is the last phase, right? Like this is where you reach, and I'm going to finish quickly after this. This is where you reach excellence. You reach excellence both at the organizational level. You improve your teams. You have a very good process for hiring good people. You have a very good process for training existing engineers and product managers, like internal, to be AI engineers or AI product managers. So you have the process, you have experience, you have the use cases, where to embed them. And you also, I call it the model deployment flywheel. So you have excellence in infrastructure, excellence in deployment for both data pipelines, as well as the full AI and ML lifecycle. So what does this mean? Concretely, it means you have very low error rates. You have a flywheel, essentially. That's what we call it. So you are able to excel at scale. And this is where you start to care about efficiency, like how efficient is your infrastructure, how much is it costing you, and you start to care about actually earning, right? So this is the last phase. One thing to keep in mind here is like, what are the roles that you need to cover when you build, like when you go to this phase or even phase 2? Like the role, the landscape of skills and roles is shifting quickly. Previously, we talked about data scientists. In Silicon Valley, there is a much more nuanced landscape of roles. To me, a data scientist is a person that sort of, can open a notebook, do a bunch of experiments with, models and data, and then do a presentation. So they don't know very well how production systems work. So that's a data scientist typically. They're not very useful for production use cases, for this whole complexity that comes after you produce a model. There's this thing called a new name called ML and AI engineers. So ML and AI engineers are actually a hybrid of a person that knows machine learning well, knows the intricacies of doing things at scale, transforming, sourcing, transforming data at scale, writing tests, and knows the infrastructure as well, right? Knows what are the limits of the deployment infrastructure of inference, like what can you throw out there, what you cannot throw out there. So they are the DevOps of machine learning and AI. And then there is this role of product managers, very important. Whereas data scientists and machine learning engineers and other roles are involved in the coding, like they essentially care about how to bring a model or how to bring a use case to production. Product managers are the ones who define what to bring to production, like what tasks should a model solve, what problem should it solve. In Europe, not very well-defined role. Typically, you don't have like software product managers, dedicated role for product managers. You need very well-trained AI product managers. Like these people actually need to know not necessarily the intricacies and how a model is trained and built. They need to have AI fluency. They need to know the major concepts, and they need to know very well in terms of how do they do experimentation, how a model affects particular subgroups in like within that larger group that you throw a model to. There are subgroups that are typically affected adversely. They need to know very well. They need to know the metrics that are involved with measuring performance and measuring, quality in all its aspects that I mentioned. So the metrics that are, for example, associated with ranking, there are typical online and offline metrics, NDCG, I don't know, MRR, et cetera, et cetera. So these guys need to know about this because they need to make the decision. Is a model good enough, not good enough? What kind of test suites do we need? What kind of quality do we need? And they study the market, right? So what does the market need? What does the user need? Okay, so this is sort of the three major roles that you can have. There are more, of course, but there is AI researcher, et cetera, for larger companies that actually do research. But in essence, you need people that do care about the how to bring something, how to build something, and people that care about what needs to be built. So this is the major distinction. And yeah, this phase of excellence is about roughly, this takes, I mean, if the first phase takes 6 months, 8 months, the second phase takes anywhere between a year and a half to 2 years to actually gain experience with scale. This phase is like what comes after these two phases, always very various. You can't put a number on it, but it's continuous. Like how to keep excelling all the time. You have to learn all the time. You have to adapt all the time. So it can take years. Anyway, so what about SMEs? This is the last slide. First challenge for SMEs is like, how do you even hire a high quality AI team? Typically, a high quality AI team is hard to get. They are also expensive. So one way to do it is to train your team. So you have to go through trainings. Ideally, for the use cases, so you have to train engineers into ML engineers. It's doable within 6 months or so. Also, another thing that you can do is to get technical and architecture advice on board, especially for this scale of scaling, for this phase of scaling and excellence. How you do it is you like, this is one of the things that I do. I advise startups. I sit on their boards, and when they make important decisions, I tell them, do it this way, do it this way. Like, or I help them with hires, like to hire someone, because they don't know. The founders have typically know they may be good on product, like they know what product to build, but they don't know how to test an AI engineer, how to test an ML engineer. So like one advice I give them is go find network and bring in these industry leaders that have some name, are well known in the local community at the very least, and bring them in as on board as advisors. You don't have to pay them anything. Typically they do it. They're just sort of as mentors. There are also non-monetary ways of compensation, right? Like especially if you are in a startup, you don't have necessarily money or good funding. So this is a very good strategy to use, because these are the people that help you through that first phase. Get the first high quality hires, and then build the first POCs. Also with networking, they can help you a lot. It's a good strategy, very widely used in startup ecosystems. Okay, this was it. One last announcement. The EUROCC Austria, we're doing a training series on foundations of LLM mastery. There is one close by, 22 January 2025, on fine-tuning on one GPU. Like, you can take a picture of this screen, and then if you're interested, and then attend it. But and yeah, like, this is the first of a series. There will be more. That is it. I went a little bit over time, but hopefully this was interesting to you, because it's a different perspective.
Thank you, Andrew. It was really a good, let's say, product journey.
Yes.
For AI. So if there are any questions, somebody, Sebastian, asked if you have any chance and time to explain the concept behind the multi-armed bandit.
Yeah, I can explain it. So multi-armed bandit is essentially it's typically used for in various use cases where you want to test different configurations, different, like let's say that is actually optimized for even a single user, right? So which means you have to deal with millions. If you have a large user base, you have to deal with millions of configurations, and you have to optimize, right? Like for each single user at the very, at the very end of the scale. Typically, you're not optimized for a single user, but for a bunch of them. But what's important is the cardinality increases significantly, right? So you don't have just a model anymore. You have a model plus all these configurations that affect the model behavior, and how you find the most optimal configuration is via these multi-armed bandits, right? Systems, right? That's it. Yeah. I mean, read about it. It's an interesting thing to read about. I cannot explain it in 1 minute. Yeah.
Sorry. Okay. And a personal curiosity for Sebastian also. Have you met use cases not based on NLPs?
Use cases that is not NLP. Yeah, I mean, as I said, NLP and like especially large language model, generative AI is very new. We've done AI for a long time, especially the classic AI search recommendations, right? Like, so those are classic use cases. Those are the money makers actually. So and there we use typical non-NLP models, right? Like they're neural networks, two-tower architectures, and so on and so forth. Recommendation models, there are ranking models, there are collaborative filtering models, and so on. So these are all non-NLP use cases. They are actually, as of today, they are the proven use cases of AI. Gen AI is not proven yet. Like, we don't know if it's going to work well for something. It looks flashy, it looks good, but actually it still needs time to evolve into products that make money, that bring value. Like, we have lots of hopes, yeah, but we don't know yet because it's too new.
Yeah, one question from Andrei Bugaev. In EUROCC calls, there is usually PyTorch and MPI plus Slurm. But there is no Spark, only Meluxina mentioned it. So should we focus more on MPA, or should we stick to a very limited set of HPC clusters supporting Spark? Today we see Spark almost in every presentation, but no MPI mentioned.
Yeah, I think this depends a lot. Like again, where does HPC fit for you? Right, like HPC fits if you have to train a large model, and like the model being large or the data being large. That's where you have to think about. Okay, HPC might be a good fit for this. Number one, number two, where you have to retrain, where you don't have to retrain very often. Because as soon as you have to retrain very often, every week, for example, you cannot go to an HPC center every week and manually take the model that is the output of the training and go and bring it to your own production. So if these two conditions are met, relatively large model plus you don't have to retrain very often, then HPC is a thing. It fits with your use case. Then I think it's worth trying to actually deploy, not deploy, but even use, hack Spark into HPC if you still want to stick with Spark. But considering that the frequency of trainings is not very often, I would not go through that route. I would say, stick to Slurm. Perform your training because, like as I said, right, like it makes sense only when you don't have to train very often. So if you're doing it once every 6 months, it's not worth it actually to go and deploy Spark there. But you're right, as in Spark support is important, and beyond even Spark. Right? Spark is, again, it caters to the training side, and there are ways to hack to sort of run Spark on HPC. But I'd say if HPC does not support deployment, and as I said, right, like there are various efforts to actually do that, to provide support for deployments for inference on HPC. HPC is limited for using AI, right? Like unless it covers the whole lifecycle stages, it is only limited to a particular few use cases, right? Where those two conditions are met. You don't retrain very often, number one. Number two, you have to produce a very large model. So yeah, I feel your pain that with Spark it doesn't support it. Yeah.
Yeah, many hosting entities have some problems. Yeah. So if there are any questions for Andrew or for the other speakers.
Yeah, shoot me an email, and the slides that I had, there is an email there for any questions. I'm glad to respond, or ask the workshop organizers for providing the contacts for me. See if anybody has follow-up questions.
Okay, one small request for all the speakers: please send your presentation to make it possible to send to all the participants. So send it to my team here, so we will make it available for them. So related to HPC AI Factories initiative, is designed to create interconnected network of AI hubs. And first 7 AI factories have been selected and are set to deploy next year. So it's in the same context of our workshop. And this will pull together the national and the European Union resources. They are trying to act as a one-stop shop, and they will offer AI startups, SMEs, and researchers support, and including access to the AI optimized HPC resources, also training and technical expertise. Sorry, can you mute your? Okay, thank you. So the fusion between HPC and AI and combined with sorry, switch off your microphone if you but if you have any question, please ask, but otherwise please mute your microphone. I'm trying to close this this session. So also we have the power of open source innovation, so that has some potential to reshape this industry and solve the challenges we face today. So thank you very much for participation and your involvement. And on behalf of NCC Romania, and all the speakers. Thank you for making this workshop a success. We'll keep in touch. As you can, so there are some trainings from NCC Austria and others NCCs on this field. So if some of them will be good for you to watch or even register. Thank you very much, and we look forward to seeing you at future events. Thank you. Goodbye.
Thank you. Goodbye.
Bye-bye. Thank you.
Thank you very much.